So welcome. In this talk, I aim to cover the entire history of mathematics in just 1 hour, illustrating my story with some of the 1,500 mathematical stamps from around the world in my collection. And I usually start by mentioning a set of 10 stamps issued by Nicaragua in 1971 and entitled 10 Mathematical Formulas That Changed the Face of the Earth. As you can see, these range from 1 + 1 = 2 and the Pythagorean theorem via Archimedes' law of moments and Newton's inverse square law, ending up with Einstein's law equals mc². You'll see some of these again later on. So let's go back in time. My treatment is chronological, going back to the time when people first began to count and measure the objects around them. Early methods included forming stones into piles, cutting notches in sticks, and especially finger counting, which led eventually to our familiar decimal number system. Also, in several places, we find ancient geometrical arrangements of stones, such as the circular pattern of megaliths at Stonehenge and the linear arrangements at Karnak in Brittany. We don't know their exact purpose, but they may have celebrated astronomical events such as sunrise on Midsummer's Day. So we'll begin our journey with the mathematical achievements of Egypt, Mesopotamia, and Greece, all shown on this map. Here's Mesopotamia, there's Egypt, and Greece further up. In Egypt, the main achievements involve the practical skill of measurement. The magnificent pyramids, designed as tombs for their rulers, attest to the Egyptians' extremely accurate measuring abilities. And the oldest of these, at the top, is King Joseph's step pyramid in Saqqara, built in horizontal layers and dating from about 2700 BC. Rather better known is the Great Pyramid of Cheops in Giza, constructed from over 2 million large blocks of stone. And amazingly, the sides of its square base, which are about 230 meters long, agree in length to within 1/100th of 1%. Our knowledge of Egyptian mathematics comes mainly from two fragile primary sources, the Moscow and Rhine papyruses, similar to the papyrus that you can see here. The Moscow and Rhine papyrus include tables of fractions and problems in arithmetic and geometry, probably designed for the teaching of scribes. On the right, you can see the Egyptian god of reckoning, Thoth. Moving to Mesopotamia, early examples of mathematical writing also appeared there between the rivers Tigris and Euphrates in present-day Iraq. Top left, you can see an accounting tablet from about 3000 BC, where the thumbnail indentations at the top represent numbers. Later, the Mesopotamians wrote their mathematics with a wedge-shaped stylus on damp clay, which was then baked in the sun. Many thousands of these cuneiform tablets survive and show basic arithmetic and the calculation of areas and volumes in geometry, the solving of what we now call linear and quadratic equations, and an extremely accurate value for the square root of 2. Their number system was based on 60, which we still use for measuring time. And they also studied astronomy and observed comets, such as the one we now call Halley's Comet, although the date of 2349 BC is about 2000 years out. Let's now move to more familiar territory. From about 600 BC, mathematics flourished in the Greek-speaking world of the Eastern Mediterranean. During this time, the Greeks developed deductive logical reasoning, which became the hallmark of their work, especially in geometry. Pythagoras, a semi-legendary figure, formed a school in Crotona to further the study of mathematics, philosophy, and natural science. His followers supposedly believe that all is number, quantifying many things and emphasizing the four mathematical arts of arithmetic, geometry, astronomy, and music, which we'll meet again later. We don't know who first proved the Pythagorean theorem, that the area of the square on the hypotenuse is the sum of the areas of the squares on the other two sides, but its connection with right-angled triangles was already known to the Mesopotamians 1,000 years earlier. The blue stamp was issued very recently in August for the International Congress of Mathematicians in Korea. The scene then moved to Athens, which became the most important intellectual centre in Greece, numbering among its scholars Plato and Aristotle. In 387 BC, Plato founded a school in a suburb of Athens called Academy, and Plato's Academy soon became the focal point for mathematical study. It's said that over the entrance appeared the inscription, "Let no one ignorant of geometry enter here," like the Greek inscription at the entrance to this very building. In Raphael's fresco, The School of Athens, on the left, Plato and Aristotle appear together on the steps of the Academy. Plato believed that mathematics and philosophy were essential training for those holding positions of responsibility, discussing the mathematical arts of arithmetic, geometry, astronomy, and music that I mentioned before, and justifying their importance. He also described the 5 regular or platonic solids shown here in the middle. His pupil Aristotle helped to formalize the study of deductive reasoning, explaining why the square root of 2 cannot be written as a fraction, and also discussing logical syllogisms such as all men are mortal, Socrates is a man, therefore Socrates is mortal. Around 300 BC, following the military successes of Alexander the Great, mathematical activity moved to Alexandria in the Egyptian part of the Greek world. The first important mathematician there was Euclid, shown on the right, mainly remembered for his Elements. This most influential compilation of known results consisted of 13 books on plane and solid geometry, arithmetic, and number theory. A model of deductive reasoning, it started from initial axioms and postulates and used rules of deduction to derive new results in a logical and systematic order. And we mustn't forget Archimedes from Syracuse in Sicily. He was one of the greatest mathematicians of all time. Around 250 BC, he calculated volumes of solids such as spheres and cylinders. He listed the 13 Archimedean or semi-regular solids. These are polyhedra with regular faces, but of different types. And he also obtained a good approximation for pi by considering 96-sided polygons that approximate a circle. In mechanics, he found the law of moments for a balance that you can see on the right, and he's also credited with inventing the Archimedes screw for raising water from a river. In statics, he stated Archimedes' principle on the weight of an object immersed in water, as you can see in the middle, and he used it to test the purity of King Hero's gold crown. On discovering the principle, he supposedly jumped out of his bath and ran naked through the street, shouting, "Eureka, I have found it." But sadly, no stamp has ever been issued featuring that particular episode. We now move to China, where the mathematics dates back some 3,000 years. Around 220 BC, in particular, the Great Wall was a major triumph of engineering skill and mathematical calculation. Most ancient Chinese mathematics was written on bamboo strips. And you can see an example top left showing a 9 by 9 multiplication table. For their calculations, the Chinese used a form of counting board, shown bottom left. A box with separate compartments for units, tens, hundreds, etc., into which small bamboo rods were placed in order to do the calculations. Chinese mathematicians were fascinated by pi. Around AD 100, Zhang Heng, who is the first of the three Chinese mathematicians you see up there, Zhang Heng, inventor of the seismograph for measuring earthquakes, he gave the value square root of 10, which is about 3.16, which was a popular approximation in many areas. Later, Liu Hui, in AD 263, shown in the middle there, considered polygons with 192 sides to deduce that pi lies between 3.1410 and 3.1427. And here you can see in the middle Liu Hui's 9th chapter of the mathematical art, his edition of that. Then around the year 500, top right, Zhu Shongxi and his son considered polygons with about 25,000 sides to obtain pi to 6 decimal places. And they also found the value 355 over 113, also correct to 6 decimal places. And this approximation wasn't rediscovered in the West until the 16th century. But a similar situation occurred with Pascal's triangle of binomial coefficients, shown here, bottom right, which had appeared in a Chinese text of 1303, although in fact it was known earlier than that elsewhere. But even so, this was 400 years before Pascal. An ancient Chinese story of perhaps 1100 BC concerns Emperor Yu, who was standing on the banks of the river Luo when a turtle emerged with 1 to 9 on its back, with the numbers in each row, column, and diagonal adding to the same sum, 15. This arrangement of numbers, the Luo Shu, acquired great religious and mystic significance, and eventually led to larger such magic squares, as pictured on these Macau stamps issued only last month. Next year, 3 more stamps will be issued by Macau with the values 816, so that the stamp values themselves will form the Luo Shu magic square, 492357 816. They obviously have a mathematician in the Macau post office. Indian mathematics can be traced back to about 600 BC, when Vedic manuscripts presented early work on arithmetic, permutations and combinations, number theory, and the extraction of square roots. And around 250 BC, King Ashoka, ruler of most of India, became the first Buddhist monarch. And in celebration, pillars were constructed. You can see one on the left, and then above you can see the capstone at the top of it, showing the earliest examples of what became our Hindu-Arabic numerals. A decimal place value system with the position of each digit 0 to 9 indicating its value, and enabling one to carry out calculations 1 column at a time, as we do now. The first outstanding Indian mathematician was Aryabhata around the year 500, who showed how to sum arithmetic progressions and also to sum the natural numbers and their squares and cubes. There's no stamp featuring Aryabhata, but there is one showing the first Indian space satellite, which was named Aryabhata in his honor. In later years, Indian mathematicians and astronomers constructed magnificent observatories, such as you can see on the right, such as the Jantar Mantar in Jaipur, comprising 14 massive measuring instruments. It included the 90-foot Samrat Yantra, the world's largest sundial. We move now to the mathematics of the Arabs and Persians. United by their new religion, and with Baghdad lying on the east-west trade routes, Islamic scholars from 750 to 1200 developed Greek and Roman writings from the west and Hindu writings from India. And some of our terminology dates from this period. The word algorithm a step-by-step procedure for solving a problem, comes from al-Khwarizmi, shown on the left, a Persian mathematician who lived in Baghdad and wrote influential works on arithmetic and algebra. His arithmetic introduced the Indian decimal place value system to the Islamic world, while the title of his algebra book, Kitab al-Jabra wal-Muqabala, gives us the word algebra. Al-Jabra means adding a positive term to both sides of an equation to eliminate negative terms. Also influential among Islamic works were those of the geometer Ibn al-Haytham in the middle. Known in the West as Al-Hazen, he mainly worked in optics. And a celebrated problem is Al-Hazen's problem, where on a spherical mirror is light from a given point source reflected into the eye of a given observer. A century later, the mathematician and poet Omar Khayyam, on the right, wrote a celebrated algebra text with the first systematic classification of cubic equations and a discussion of their solution. They weren't solved in general until 16th century Italy. Omar Khayyam also publicly criticized an attempt by Al-Hazen to prove Euclid's so-called parallel postulate, which I'll be explaining later. In the West, he's mainly remembered for his collection of poems, the Rubaiyat. A later unsuccessful attempt to prove Euclid's parallel postulate was by the Persian mathematician Nasir al-Din al-Tusi, shown on this magnificent stamp there on the left, who wrote substantial works on astronomy and constructed the first modern observatory. He also wrote influential treatises on logic and theology, and his extensive investigations into plane and spherical trigonometry included the sine rule for triangles. During the 8th and 9th centuries, the Islamic world spread across the top of Africa and then up into Europe through Spain and Italy. Cordova became the scientific capital of Europe, while Islamic decorative art and architecture spread through southern Spain and Portugal and included the magnificent geometrical arches in the Cordova Mosque, which you can see on the left, and the tiling patterns in the Alhambra in Granada on the top right. Also in Cordova, the geometer and astronomer Al-Zarqali, shown in the middle at the bottom, constructed many astrolabes. These consisted of a brass disc suspended by a ring that's fixed or held in the hand, with an attached rotating bar and a circular scale on the rim. And to measure the altitude of a planet or star, you view it along the bar and then read the result from the scale. But in Europe, the period from 500 to 1000 was known as the Dark Ages. The legacy of the ancient world was largely forgotten, and the level of culture was low. But revival of interest in mathematics began with Gerbert of Aurillac, who trained in Catalonia and introduced the Hindu-Arabic numerals to Christian Europe, using an abacus he designed for the purpose. A major figure in the church, he was crowned Pope in the year 999. That doesn't happen to many mathematicians. Top right, the Catalan mystic Ramon Lull believed that all knowledge can be obtained combinatorially by taking mathematical combinations of God's divine attributes, such as power, wisdom, goodness, etc. His combinatorial ideas later spread throughout Europe, influencing such mathematicians as Mersenne and Leibniz. And a surprise appearance here is Geoffrey Chaucer, author of the Canterbury Tales, who also wrote on the astrolabe. This was one of the earliest scientific books in English. The Hindu-Arabic numbers were also popularized by Fibonacci, or Leonardo of Pisa, in his Liber Abaci, Book of Calculation. This famous work of 1202 contained many problems in arithmetic and algebra, including his rabbit's problem on the left, that leads to the Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, and so on, in which each successive term is the sum of the previous two. These numbers also arise in the arrangements of seeds in sunflowers and pine cones. For example, there's a sunflower head there, and if you count round the spirals, you get numbers like 55 and 89 appearing. The ratios of successive terms of the Fibonacci sequence approach a limit, the golden ratio, which is about 1.618. It's the ratio of a diagonal and a side of a regular pentagon, and also a rectangle with sides in this ratio is sometimes considered to have the most pleasing shape, not too thin and not too fat. As shown on the Swiss stamp, top line in the middle, removing a square from a golden rectangle leaves another one. And this stamp also features the logarithmic spiral found on the Nautilus shell below. But also in the set from Macau is a stamp featuring a Penrose tiling, which I thought I ought to show you today, consisting of its two shapes, the kite and the dart. And if you want to see a Penrose tiling, you don't have to go very far. There's a big one just outside this building, as you know. The Renaissance in mathematical learning in the Middle Ages was mainly due to three things: the establishment of universities, the translation of Arabic texts into Latin, and the invention of printing. The first European university was Bologna, shown top left, founded in 1088, with Paris and Oxford following soon after. What was taught? The curriculum was in two parts, the second of which led to a master's degree and was based on the quadrivium. You can see the quadrivium subjects on the right, the Greek mathematical arts, again, of arithmetic, geometry, music, and astronomy. And the curriculum also included the study of Ptolemy's Almagest and Euclid's Elements. Gutenberg's invention of the printing press around 1440 enabled mathematical works to be widely available for the first time. At first, they were printed in Latin for the scholar. But gradually, vernacular works in the language of the people appeared at prices accessible to all. And these included texts in arithmetic, algebra, and geometry, as well as practical works to prepare their readers for a commercial career. And important among these, you can see on the top right, was Pacioli's 600-page Italian Summa, a compilation of the mathematics of the time, which also included the first published account of double-entry bookkeeping. And then below that, a commercial arithmetic by Adam Riese, which was so respectable that the phrase nach Adam Riese, after Adam Riese, came to refer to a correct calculation. The invention of printing led gradually to standardization of mathematical notation, and the symbols plus and minus first appeared in print in an arithmetic text of 1489, whereas the symbols for times and divide didn't appear until considerably later. It was around this time that painters learned how to give visual depth to their works through geometrical perspective. The first to investigate this were Brunelleschi, who had designed the dome of Florence Cathedral, and his friend Alberti. They're both shown at the top on the left. Alberti gave mathematical rules for correct perspective, and he stated that the first duty of a painter is to know geometry. So if you have any artist friends, you know what to tell them. Bottom left, Piero della Francesca used a perspective grid for his geometrical studies, and his Madonna and Child with saints, shown here, is in perfect mathematical perspective. The polyhedron woodcuts that appear in Piero's books were actually by Piero's friend and student Leonardo da Vinci, shown on the top right, who investigated perspective more deeply than any other Renaissance painter and warned, "Let no one who is not a mathematician read my work." Another celebrated artist was Albrecht Dürer at the bottom, who learnt geometrical perspective from the Italians and introduced it to Germany. And his engravings, such as St. Jerome in his study, show his mastery of it. We now turn to navigation. The Renaissance period coincided with the great sea voyages and explorations of Vasco da Gama, Columbus, and others. The Portuguese explorers sailed south and east. Prince Henry the Navigator, on that wonderful stamp at the top, sent ships down the west coast of Africa, claiming the island groups of Madeira and the Azores. And Vasco da Gama was the first European to sail around the tip of Africa to reach the west coast of India. Their rivals, the Spanish, headed west, hoping to reach India by sailing around the globe. And Columbus led 4 such expeditions, but instead reaching North and Central America, the West Indies, and Venezuela. And you can see Columbus, the bottom right. Such explorations inevitably needed accurate maps and reliable navigational instruments for use at sea. But trying to represent the spherical Earth on a flat sheet of paper led to new types of map projection and to improved maps for navigators at sea. The first modern maps used the Mercator projection, obtained by projecting the sphere outwards onto a vertical cylinder and then stretching the scale vertically so that all the lines of latitude and longitude appeared straight, while all the angles and compass directions were correct. And you can see here Mercator, you can see the Mercator projection, and also the Canadian stamp of 1898 at the top also features it. Incidentally, Mercator was the first person to use the word atlas for his 3-volume collection of maps in 1590. But for navigation at sea, you needed instruments. Astrolabes were widely used, as were quadrants, sextants, octants, and other instruments. They were used to measure the altitudes of heavenly bodies, such as the sun or pole star, in order to determine latitude. Quadrants, on the top left, have the shape of a quarter circle, 90 degrees, while sextants, in the middle, correspond to a sixth of a circle, 60 degrees, and octants, bottom left, to an eighth of a circle, 45 degrees. To measure an object's altitude, you view it along the top edge of the instrument, and the position of a movable rod on the rim gives you the result. Earlier, Levi Ben Gerson had invented the widely used Jacob staff or cross staff for measuring angles between celestial bodies, which you can see on the top right. But unfortunately, to measure the angle between the sun and the horizon, you had to look directly at the sun. The back staff, shown below it, was a clever modification where you had your back to the sun. We'll now move to astronomy, which was completely transformed when Copernicus replaced the Greeks' Earth-centered system of planetary motion by a heliocentric one with the sun at the center and the Earth as just one of the planets in circular orbits around it. His book on the revolution of the heavenly spheres was published in 1543, and a copy of it was supposedly presented to him on his deathbed. The Copernican system aroused much controversy, bringing its supporters into direct conflict with the Church, who considered Earth to lie at the center of creation. And several were arrested by the Inquisition or even burnt alive for heresy, such as Giordano Bruno. Indeed, at a famous Inquisition trial in 1633, Galileo was placed under house arrest after his dialogue concerning the 2 chief world systems had presented the Copernican system as superior to the Ptolemaic one. Galileo wasn't pardoned by the Church until 1995, which was a bit late to do him much good. Galileo was the first to make extensive use of the telescope. He wasn't the first to use it. I think that claim goes to Harriot in Oxford just a few months earlier. But anyway, Galileo drew the moon's surface and discovered the moons of Jupiter and Saturn. And you can see one of his drawings on the left. In his mechanics book, Two New Sciences, he discussed uniform and accelerated motion, and explained why the path of a projectile must be a parabola. But the greatest observer of the heavens before the invention of the telescope was the Danish astronomer Tycho Brahe. In his observatory in Uraniborg, on the island of Havane, which I had the pleasure of visiting this summer, he designed astronomical instruments of unequalled accuracy and measured over 700 stars. And in particular, he discovered a new star, or nova, in the constellation of Cassiopeia. Johannes Kepler, shown here at the bottom, who worked with him, is mainly remembered for his 3 laws of planetary motion. Using Tycho Brahe's extensive observations, he was led to consider non-circular orbits, proposing that the planets move in elliptical orbits with the Sun at one focus, and that the line from the Sun to any planet sweeps out equal areas in equal times. Kepler was fascinated by ellipses and other conics, and he was the one that introduced the word focus into mathematics. Rotating such curves around an axis, he found the volumes of over 90 solids of revolution by summing thin disks, thereby anticipating the integral calculus a few years later. But a major problem of the time, particularly for astronomers and navigators, were difficulties of calculation. In 1614, 400 years ago this year, John Napier of Edinburgh introduces logarithms, designed to replace lengthy multiplications and divisions by easier calculations with additions and subtractions. Being awkward to use, for example, Napier's log of 1 was not 0, they were soon supplanted by Henry Briggs's simpler logs to base 10, produced while here in Oxford, whose use proved of enormous benefit to astronomers and navigators. The invention of logarithms soon led to practical instruments based on a logarithmic scale, such as the slide rule shown on the right. Dating from about 1630, they were used for over 300 years until pocket calculators started to appear around the year 1970. The first mechanical calculating machines were also introduced around this time, and in 1623, one was described by William Schickhardt on the orange stamp in letters to Kepler, while later machines were constructed by Pascal and Leibniz. Pascal's machine, the Pascaline, was operated by cogged wheels and could add and subtract numbers, while Leibniz's could also multiply and divide, but neither instrument worked particularly well in practice. We'll now move to 17th century France, to Descartes, Fermat, and Pascal. An ancient problem of Pappus had asked for the path of a point moving in a specified way relative to some fixed lines. To solve this, Descartes named 2 particular lengths, x and y, and calculated every other length in terms of them, obtaining a quadratic expression, that is a conic, as the required path. Descartes thus introduced algebraic methods into geometry, but he didn't initiate the Cartesian coordinates named after him, in which the angles are at right angles, points appear as pairs of numbers x, y, lines are equations y equals mx plus c, and to find the intersection of 2 lines, you solve 2 simultaneous algebraic equations. Descartes' most celebrated work was his Discourse on Method, a philosophical treatise on universal science containing his contributions to geometry. 300 years later, France issued a stamp to commemorate it, the one on the right at the top. But they got its title wrong, Discours sur la méthode. The sur was later corrected to de on a later stamp shown below. Still in France, Fermat, a lawyer in Toulouse, is mainly remembered for his contributions to number theory. In particular, he famously claimed to have proved that the equation x to the n plus y to the n equals z to the n has no non-zero integer solutions when n is greater than 2. And this result came to be known as Fermat's last theorem and was eventually proved by Andrew Wiles in 1995, as shown by the red bar across the equal sign, which says Andrew Wiles 1995. Pascal showed an early interest in mathematics. At the age of only 16, he discovered his hexagon theorem, about 6 points on a conic joined up in a particular way. Pascal's principle in hydrodynamics is named after him, and he was one of the first to investigate the theory of probability. He also wrote about the arithmetical triangle of binomial coefficients, and Pascal's triangle appears on the pink stamp here, another one from the recent International Congress of Mathematicians in Seoul in Korea. Isaac Newton was born in 1642. In Cambridge, he avidly studied such contemporary works as a Latin edition of Descartes' Geometry and was appointed Lucasian Professor of Mathematics, a post later held by Stephen Hawking. The story of Isaac Newton and the apple is well known. Seeing an apple fall, he proposed that the gravitational force pulling it to Earth is the same as the force that keeps the moon orbiting around the Earth and the Earth orbiting around the sun. He also claimed that this planetary motion is governed by a universal law of gravitation, the inverse square law. The force of attraction between two objects varies as the product of their masses and inversely as the square of the distance between them, as shown on this stamp here. In his 1687 Principia Mathematica, perhaps the greatest scientific work of all time, Newton used the inverse square law to justify Kepler's laws of elliptical planetary motion and to account for cometary orbits, the variation of tides, and much else besides. But the Principia would never have appeared if Edmund Halley hadn't cajoled a reluctant Newton into developing his ideas of gravitation and publishing them. Halley himself paid for this. Halley, of course, later became Savilian Professor of Geometry here in Oxford. So Halley, or possibly and probably Hawley, but definitely not Halley, is mainly remembered for the comet named after him. Observing it in 1682, he realized it was the same as one seen many times earlier. He predicted its return in late 1758, and its appearance then, several years after his death, did much to vindicate Newton's theory of gravitation. And because of his prediction, it became known as Halley's Comet. There are quite a few stamps featuring Halley's Comet. I like the British one, top right, which has Halley's head as the head of the comet and his wig as the tail. But reactions to Newton's approach to gravitation were mixed. In England, his Principia was well received, even though few readers understood it, but not everyone was receptive, particularly in France. The Principia was long and difficult and raised awkward questions about the shape of the Earth. Descartes had earlier proposed a vortex theory of the universe, a consequence of which is that the Earth is elongated at the poles, that is, lemon-shaped. Newton criticized Descartes' ideas in the Principia, predicting a flattening at the poles so that the Earth is onion-shaped. National pride was at stake, and the matter was urgent because inaccurate map-making was leading to the loss of lives at sea. Eventually, two geodetic missions were dispatched to settle the matter by measuring the swing of a pendulum at the equator and near the North Pole. De la Condamine's mission on the left went to Peru and included the Spanish mathematician and cosmographer Jorge Juan, while Maupertuis's mission travelled to Lapland. But eventually they confirmed Newton's theory. The Earth is indeed flatter at the poles. Although Newton could justly claim priority for the calculus, Leibniz, who developed it independently, was the first to publish it. Also, his notation was more versatile than Newton's, And amazingly, his dy by dx for differentiation and the integral sign were introduced by him within 3 weeks of each other in the autumn of 1675 and are still used today. But his calculus was rather different from Newton's, being based on geometry and areas rather than on velocity and motion. The Bernoulli family included several distinguished Swiss mathematicians, but only one, unfortunately, has been featured on a stamp. In his book, The Art of Conjecturing, Jacob Bernoulli, top left, proved the law of large numbers. When an experiment is performed often, it's highly probable the outcome is as we expect. For example, tossing a fair coin 2,000 times gives a number of heads close to 1,000. With his brother Johann, Jacob Bernoulli was the first to develop Leibniz's calculus, introducing the word integral and applying calculus to such curves as the logarithmic spiral and the cycloid. Leonhard Euler, shown on the rest of these stamps, also grew up in Basel, but spent most of his working life at the scientific academies of St. Petersburg and Berlin. The most prolific mathematician of all time, he contributed to almost every branch of mathematics and physics, including number theory, mechanics, differential equations, astronomy, and optics. Euler reformulated the calculus in terms of functions. He introduced the notations e for exponential, I for the square root of -1, capital sigma for summation, and f for a function. And he also related the exponential and trigonometrical functions through the equation e to the I phi is cos phi plus I sin phi. And if you're in Switzerland on the way to the post office and you happen to forget that formula, it's on the top right stamp up the side. In 1750, he discovered his polyhedron formula, faces plus vertices equals edges plus 2, shown the 2 stamps on the bottom left. And in 1735, he solved the famous Königsberg Bridges problem, which asked whether one can cross all of the 7 bridges of the city of Königsberg without visiting any bridge twice. But he didn't draw the graph that's shown here on the recent Korean stamp, also for the International Congress. Back now to France, where the turbulent years of the French Revolution and the rise to power of Napoleon led to important developments in mathematics. Napoleon himself was greatly interested in the subject, and one of his greatest friends was the geometer Gaspard Monge, whom you can see on the left underneath, who had taught at a military school where he studied the properties of lines and planes in 3 dimensions. While investigating gun emplacements in a fortress, he greatly improved methods for projecting 3-dimensional objects onto a plane. This subject soon became known as descriptive geometry. An important consequence of the French Revolution was the founding in Paris of the École Polytechnique, shown top right. There, the country's finest mathematicians, including Monge, Lagrange, Laplace, and Cauchy, taught students designed to serve in both military and civilian capacities. Lagrange was Euler's successor at the court of Frederick the Great in Berlin. He wrote the first theory of functions and an influential text on mechanics, and in number theory he proved that every integer can be written as the sum of 4 perfect squares. Laplace was the applied mathematician par excellence, remembered for the Laplace transform of a function and for Laplace's equation in mathematical physics. He also wrote a celebrated text on probability, and his monumental 5-volume treatise on celestial mechanics earned him the title of the Newton of France. Shortly after the French Revolution, a commission was set up to standardize the weights and measures in France and introduce a metric system. Here you can see a French stamp celebrating the metric system. The chairman of this commission was Lagrange, and its members included Laplace and Monge. Work in analysis continued with Cauchy. The calculus had proved to be on shaky grounds, but Cauchy rescued it by basing it on the concepts of limit and continuity. He also developed complex analysis almost single-handedly, and here on the top of that stamp you can see Cauchy's integral formula, which is familiar to all second-year undergraduates. Meanwhile, in Germany, Gauss was working in many areas, from complex numbers, the Gaussian number plane shown on the right, factorizing polynomials, the fundamental theorem of algebra, to statistics, the Gaussian distribution. One of the greatest mathematicians of all time, he discovered which regular polygons can be drawn by ruler and compasses alone. These include equilateral triangles and regular pentagons, and also the 17-sided polygon shown here, which you thought was a circle. The early 19th century saw major revolutions in geometry. Euclid's Elements had commenced with 5 postulates, 4 of them straightforward, but one different in style, resembling a theorem that ought to be provable from the others. One version of it is a parallel postulate. Given any line and any point not on it, there's a unique line through the point which is parallel to the given line. For over 2,000 years, mathematicians tried to prove this from the other postulates but failed. And this is because there are non-Euclidean geometries satisfying the first 4 postulates but not the 5th. These geometries have infinitely many lines through the point which is parallel to the given one, as shown in the Hungarian stamp there at the bottom. They were first published around 1830 by Nikolai Lobachevsky from Russia and János Bolyai from Hungary. Another new geometrical object from the 19th century, actually from 1858, was the Möbius strip, shown here, which has only one side and one boundary edge. All these many developments in geometry, projective geometry, non-Euclidean geometry and so on, forced mathematicians to ask which geometry corresponds to the world we live in. Is it Euclidean geometry or is it a non-Euclidean one? In fact, the geometry that later arose in Einstein's theory of relativity was one designed by the German Bernhard Riemann, who has unfortunately never appeared on a stamp. But here are some pictures of Einstein, including the strange one in the middle of the top row. Looks as though he's just got up in the morning, with his famous equation E equals mc squared relating energy and mass shown on the wallpaper behind him. Obviously that's where he got the idea. There was also a major breakthrough in algebra when the Norwegian Niels Abel solved a long-standing problem. Recall that quadratic equations had been solved by the ancient Mesopotamians, while 16th century Italians had shown how to solve equations of degrees 3 and 4. But what about equations of degree 5 or more? Abel showed that the chain stops here. There is no general formula to solve such equations. Abel's work was extended by the brilliant young French mathematician Évariste Galois, about whom Peter Neumann has written extensively, who explained algebraically exactly which equations can be solved. Galois had a short and turbulent life, being sent to jail for political activities and dying tragically in a duel at the age of 20, having sat up the previous night writing to a colleague about containing his mathematical achievements for posterity. Below is William Rowan Hamilton, a child prodigy who mastered several languages at an early age, discovered an error in Laplace's celestial mechanics as a teenager, and became Astronomer Royal of Ireland while still a student. He made important advances in mechanics and geometrical optics, and while attempting to generalize the complex numbers, discovered the quaternions, a non-commutative system involving 3 square roots of -1, called I, J, and K, which you can see here, satisfying the equation shown on the Irish stamp. Unfortunately, not many women mathematicians have featured on stamps, but here are 2 important ones. Florence Nightingale is mainly remembered as the lady with the lamp, who saved many lives through her sanitary improvements in Crimean war hospitals. But she was also a fine statistician who collected and analysed mortality data from the Crimea and displayed them using her polar diagrams, forerunner of the pie chart. Meanwhile, Sonia Kovalevskaya was making valuable contributions to mathematics, physics and astronomy, as well as becoming a well-known novelist. Barred by her gender from studying in Russia, she attended physics lectures by Kirchhoff and Helmholtz in Germany before settling in Sweden. She later won a coveted prize from the French Academy of Sciences for a memoir on the rotation of bodies. So we've at last reached the 20th century when several mathematicians created the subject as we now know it. So here's a brief selection. The range of David Hilbert was immense, from number theory and so-called Hilbert spaces in analysis to potential theory and the theory of gases. In 1900, his celebrated lecture at the International Congress of Mathematicians in Paris described 23 problems that set the agenda for mathematical research over the coming century. Henri Poincaré, shown top left, wrote on the still unsolved three-body problem of determining the simultaneous motion of the Sun, Earth and Moon. A gifted popularizer of mathematics, he developed many areas, including algebraic topology, differential equations, celestial mechanics, and much else besides. Below him, in England, Bertrand Russell made fundamental contributions to mathematical logic, such as Russell's paradox. With A.N. Whitehead, he wrote Principia Mathematica, a pioneering 3-volume work on the logical foundations of mathematics, in which the equation 1 + 1 = 2 isn't proved until page 86. On the right, Ramanujan was one of the most intuitive of all mathematicians. Mainly self-taught, he left India in 1914 to work with G.H. Hardy in Cambridge, producing some spectacular joint work in number theory and analysis before his untimely death at the age of 32. In Poland, Stefan Banach, bottom right, helped to create modern functional analysis and to develop links between topology and algebra, and Banach spaces, Banach algebras, and so on are named after him. Another 20th century development was fractal geometry, and in 2005, Macau issued a set of stamps featuring fractal patterns. Such patterns are self-similar, reproducing themselves infinitely often when magnified or reduced. Here, top left, you can see von Koch's snowflake curve of infinite length but enclosing a finite area, and on top right, Hilbert's space-filling curve. And the series also has the Cantor set and a fractal tree and the Sierpinski triangle. When the transformation of squaring and translating, that z goes to z squared plus c, is applied repeatedly to the complex plane, some points shoot off to infinity, depending on the value of c, while the rest remain finite. The boundary between these two sets is a fractal pattern called the Julia set, after the Frenchman Gaston Julia. And the attractive Israeli stamp that you can see there shows part of a Julia set. The set of all constants C for which the Julia set is in one piece is the famous Mandelbrot set shown here on this miniature sheet. But if you prefer something a little more light-hearted, there's always the Rubik cube. Invented by the Hungarian engineer Enno Rubik, it's a color cube whose faces can be independently rotated so as to yield over 4 × 10⁻⁹ different patterns. The object is to restore the original colors. In the early 1980s, when the Rubik cube craze was at its height, over 100 million cubes were sold. Well, we're coming towards the end. Mathematics continues to advance at an ever-increasing rate, and since 1897, international congresses of mathematicians have been held around the world, at which many thousands gather for every 4 years to learn about the most recent developments in their subject. Several of these congresses have been commemorated on stamps. Here are those moving along the top row from Moscow in 1966, Helsinki in 1978 with a design from differential geometry, Kyoto in 1990 showing an origami polyhedron, Berlin in 1998 showing the division of a rectangle into unequal squares with integer sides, with the digits of pi swirling around in the background, and Madrid in 2006. This year, Korea issued no fewer than 3 stamps, all seen earlier, depicting the Pythagorean theorem, Pascal's triangle, and the Königsberg bridges problem. And a special feature of the ICMs is the awarding of Fields medals to the most outstanding mathematicians under the age of 40. Starting in 1936, they were financed from the estate of J.C. Fields, who is at the top right. He was president of the 1924 Toronto Congress. And here in the middle of the bottom row, you can see Simon Donaldson, who was awarded his Fields Medal while in Oxford, while above him is Alan Baker, the distinguished number theorist from Cambridge. So to conclude, as we look back over 4,000 years, we might emulate Time magazine's Man of the Year and ask whether the mathematician of all time has ever appeared on a stamp. Unfortunately, the answer is yes. Thank you very much.